Hey everybody, it's Mrs. Fisher. Today we're doing Unit 7, Day 2, Vector Applications. And again, for you physics folks, these aren't exactly the same applications that you do in physics. It's a little bit different. Before we begin, let me just define one term here, and that is a direction angle. That term gets thrown out a lot, and so I just want to make sure we're on the same page with that. A direction angle is the angle measured from the positive x-axis and moving counterclockwise. In other words, the same way that we've been measuring angles this entire time that we've been studying trig. This is just a different term, direction angle. We will be talking about some other ways to measure angles in our lesson today. So if we say direction angle, we mean just the normal way that we always talk about angles. All right, so an example is going to be the opposite of what we did at the end of class last time. Last time we were working, or I should just say during class last time, we were working with x components and y components and then finding what vector v was and finding its magnitude and finding the angle. So now we're going to be talking about if you have the angle, find the component form. Of the vector. Okay, so let's say you're given this picture and your angle is, let's put it like this, and we'll say that this is 19 degrees and your magnitude is listed as 17. All right, so one thing is that we've got this angle right here of 19 degrees. The direction angle, just so we're clear on what that means, the direction angle is the angle that starts at 0 and goes all the way around to where your vector is. So to figure out what the direction angle would be, it's going to be 180 plus the 19 for this one. So the direction angle is going to be 199. Okay, now that 199 can be helpful when you're doing your math for this. There's two ways you really could do this problem, so I'm going to discuss both of those ways. If I want to find the components, like I said, it's kind of the opposite of what we were doing last class. I want to know what the x is and what the y is. So I want this x1 and the y1. So again, hopefully you can see that we've got a right triangle, and if we've got a right triangle, we can do our right triangle trig stuff. So last time we were doing Pythagorean theorem to kind of figure out what the magnitude was. Here we're going to work backwards. We want to find out what the x and the y are. So to do that, we are going to utilize our SOHCAHTOA stuff. So method 1 is to use SOHCAHTOA. Okay, so if I want to find what x1 is, then I would say that that is adjacent to the 19, and I've got the hypotenuse, so adjacent over hypotenuse is going to be equal to the cosine of 19. So when we multiply, we should get that x1 is equal to 16.07. All right, But y'all should look at that and say 16.07, that's a positive number, and that would indicate that we're moving to the right. But if you look at our given vector, that's moving to the left. So you have to be smarter than the mathematics here, and in your final answer for a component for vector v would be to write down in your triangle braces negative 16.07. All right, to find the y component, you would do y1, that's opposite the 19, so opposite over hypotenuse is going to equal sine of 19. Multiply the 17 over, you'll get y1 equals 5.53. Now again, looking at the picture, I would hope you would recognize 5.53 is a number that indicates moving up when it's a y value, but our picture shows that it's below the x-axis. So we need to be smarter than the math and say that that's negative 5.53. All right, so that's method one. That's using SOHCAHTOA. This is usually how I do it. I like to draw a picture and then just use the mathematical tools that we've been using over and over and over again for a long, long time. Method two is to use a formula. So if you like to memorize stuff, then this is your way. So method two is memorize this formula. And the formula really just comes from the exact math that we just did. And that is to look and see that the work we did up here was to say that x1 was equal to 17 times cosine 19, and that the y1 was equal to 17 times sine of 19. That 17 has special significance in the formula. The 17 is equivalent to the magnitude. So that's really important. So the formula would be that vector v can be found by doing the magnitude of the vector times cosine of the angle, and then magnitude times sine of the angle. Now when we say angle in this formula, we're talking about the direction angle. So in the formula, we're not talking about 19, we're talking about 199. So to get your answer, you would do 17 cosine 199 and 17 sine 199. And if you do that, you should get the exact correct answer with the signs being accurate without really having to think. But you do have to have the formula memorized. And that works out pretty well. Look at the signs right for you because of the unit circle. And your calculator has those numbers programmed in it, so it knows what's positive and what's negative. Okay, so that brings us to something that we didn't get a chance to talk about last class, and that is I and J form. Just hadn't mentioned it. I and J form is just another way to write your components. So I is a unit vector in the x direction. And J is a unit vector in the y direction. So you might see some problems that are written out with the components not in the triangle braces. So instead of -2, 3. So you might not see it like that, but you might see it in I and J form. So that is equivalent to writing out 2I minus 3J. All right, so you might see some problems like on WebAssign, on your final exam perhaps, that will have the I and J's instead of the triangle braces. The triangle braces are way nicer to look at. So as an example, if I ask you to find the magnitude and direction angle, of this angle, or of this vector here, this vector is written as 3 cosine 60I plus sine 60J. Okay, that is just a really beat up way of writing down what this vector is. Okay, so the first thing I would do is simplify that stuff. So cosine 60, you should know what that is. And sine 60, you should know what that is. Okay, so I would simplify this whole thing and not have it look all gross. So cosine 60, a half. Sine 60, √3/2. So it still looks a little gross because we've got fractions. Multiply by 3 here, so you have 3/2 I plus 3√3/2J. So when it says find the magnitude and direction angle, well, first of all, I would hope you'd figure out what the angle was by how the problem was written. Do y'all see that there was an angle given in there? So your angle's 60. The 3 out in front is just telling you that you got everything is 3 times as big. This is what's in the parentheses. So that doesn't really affect your direction angle at all. The 3 times cosine 60 and 3 times sine 60. If you remember, this 1/2 is the length of x on the unit circle, and this √3/2 is the length of y on the unit circle. So what is this 3 really representing? The magnitude. Yeah, because it's 3 times bigger than the values that are on the unit circle. So this is actually a trick question. The magnitude here is actually 3. That question was tricky and gross. All right, so let's talk about the applications, which we will do a bunch of practice with in class. And you will love. So applications, we're going to deal more with things like boats moving in a current, airplanes flying through the air with a wind current, things like that. So we're really going to be thinking about vector as the velocity of those things. Okay, so we're going to use vectors to represent velocity. Okay, the magnitude of that is going to be the speed. So anytime they talk about speed, they're really helping you get the magnitude of the vector. And the other really important thing here is that the angle, whenever we're talking about things that are moving and taking direction and navigation, they don't use normal angles like we've been using in trig. They talk about compass angles. And so when they talk about the compass, north, south, east, west, north, south, east, and west, north is your 0 degrees. And then we move around clockwise. And this is called a bearing. So they'll talk about the compass bearing to describe the angle. So that is the biggest issue with our application problems, is that our angle gets measured going from a completely different start point and in a completely different direction from how we've been measuring angles this whole time. So, an example. A jet aircraft is flying on a bearing of 65 degrees at 500 miles per hour. Find the component form of the airplane. Okay, so this is pretty straightforward because it's just like the problems we've been doing. The only difference is how we are going to label our angle. So we've got this 65 degrees right here. The difference is when we make our picture, you always want to make a picture. 0 degrees is north when we see this word bearing. Okay, so you start up there and then you measure going clockwise. So 65 degrees is going to go here. That means your other angle, where we're used to looking at angles, is going to be 25 degrees. Okay, 500 miles per hour, that velocity, that is going to be the magnitude of your vector. So we know the length of this vector is 500. Okay, so now when we do our math, we're still going to do our math the same way we always have. We're going to bring down a triangle down to the positive x-axis here. Make a little right triangle. And to find the components, here's your x1, your y1, and you want to do the same thing that we're just doing in these last examples. I don't care which method you do. You can do SOHCAHTOA. You can do the formula. I don't really care. Your direction angle, though, is the 25. So if you want to find the components using that formula, we can just do 500 cosine 25, 500 sine 25. It's pretty easy. But that's just using the formula that we wrote down before. And when you solve that, you get 453.15 and then 211.31. And those are the components. Now, the reason we care about having components is so we can actually do a legit problem, because we didn't really do a real problem there. So let's look at an actual problem. Okay, so let's look at this. A plane is flying due east at 5 507 miles per hour. The wind is blowing at 65 miles per hour. At a bearing of 60 degrees. Find where the plane will actually head and at what speed. All right, so because there is a wind in this problem, the wind is going to affect how the plane is going to end up really flying. So the plane's trying to fly at 507 miles per hour. The wind is blowing at 65, so it's going to alter the plane's speed. It's going to alter the plane's path. Okay, so the pilots adjust for this sort of thing, but this is basically what's happening. So again, we are going to draw a picture. Okay, so this is going to be my plane picture. Okay, the plane is flying due east. So first of all, let's understand what due east means. Due east means I'm flying to the east, just straight up east. So there's no angle there. It's just straight east. 507. Now there's a wind. So I'm going to draw another picture for the wind. Wind is going to go it's a bearing of 60. So again, that means that, wind is not that big. So my vector should be smaller. But the wind is going 60 degrees. So that means from here to here should be 60. All right, and the magnitude of that is 65. Okay, that means right here, this angle's 30. Sorry, that got a little crowded in there. So we want to know the result or the resultant of these two forces acting together. So this is where we want to do some mathematics like we did on the first day. And we want to add these two forces together and see what the actual path of the airplane is going to be. Find where the plane will actually head and at what speed. Okay, so the wind going to be there. So what you want to do is you want to make components. So for the plane, it's pretty easy. We can't make a triangle. We are going straight to the east. So we are going 507 in the x direction, 0 in the y direction. For the wind, you are going to have to do your little formula thing. 65 cosine, and then your direction angle. That's 30. And then 65 sine 30. Now to figure out the result of these two forces acting together, you add. Can y'all hear my dog barking? This seems to always happen. So you want to pull out your handy dandy calculator. You want to figure these out. I do not have these already figured out. So you want 65 cosine 30. And then 65 sine 30. All right, and then we're going to add the two together. Oh, now you could probably hear people talking in my house. Okay, so add together and we get 563.3 and 32.5. So this is where the plane is actually heading. So it's going 563.3 east and 32.5 north, basically. So you could draw a whole new triangle. A whole new triangle with that. Same 563.3 east and 32.5 north. So something like that. I have no idea. Not drawing it very accurate. But if you know that this is 563.3 and you're going up 32.5, how can we figure out what the new speed would be? You'd find the magnitude, Mrs. Fisher. That's right, guys, you would. So you'd find the magnitude. So new speed is going to equal the 563.3 squared plus 32.5 squared, and then take the square root of that. So let's do that. So let's see, 32.5 squared. And then the square root of that. This is a gigantic number before you square root it, I can tell you that. All right, so I'm getting 564.2 miles per hour. That seems wrong. Oh, no, sorry. It was a 65 mile per hour wind. That's a fast wind. I thought, man, the wind couldn't change it that much, but it was a strong wind. So, yes, 564.2. You always do want to check and make sure your answer seems reasonable. Sometimes people tell me it's going to be like 1,000 miles per hour. So definitely make sure your answer seems reasonable. Okay, so we will be working on more problems like this, but your basic formula for you formula lovers, all we did here was we said plane plus wind equals the resultant. It's pretty easy. Your plane components plus your wind components equals your final path. And that's all she wrote, folks. Have a good one.